Welcome to this technical deep dive into Zeno-Energy. Today, we are exploring a research paper by Dana Edwards that addresses a critical efficiency problem in decentralized exchange settlement. By the end of this video, you will be able to explain the model proposes, verifier decides architecture, and describe how energy-based ranking reduces computational waste in search problems. The core question the paper asks is, can a tiny, learned energy scorer reduce the cost of finding the best settlement candidate while leaving the deterministic verification process completely unchanged? As we will see, the answer is a definitive yes, with significant implications for high-throughput trading systems. To understand why Zeno-Energy is necessary, we first need to look at the settlement problem in Zeno-DEX. In a settlement context, denoted as X, we have a finite set of potential candidates, which we call C of X. For every candidate, there is a deterministic verifier, V sub X of C, which tells us if a settlement is valid. There is also an objective function, J sub X of C, which measures things like executed volume and surplus. The goal is to find the exhaustive verifier winner, C star. This is the candidate that maximizes our objective while being accepted by the verifier. The problem is that in an exhaustive search, we might check dozens of candidates before finding the winner. If the winner is at the end of the list, we waste a lot of computational power on verifier calls. Zeno-Energy aims to reorder this list so the winner appears first, minimizing those expensive calls. Zeno-Energy solves this by learning a scalar energy value for each candidate. We define an energy function, E sub theta of X and C, that maps a context and a candidate to a real number. The fundamental rule here is that lower energy means higher priority. If the model thinks a candidate is likely to be the winner, it assigns it a lower energy score so it gets verified earlier. The optimization target for training this model is to minimize the expected position of the actual winner, C star, after the candidates are sorted by their energy scores. Crucially, the settlement rule itself remains untouched. The verifier, not the model, has the final say. The model is merely an advisor, suggesting which candidates to look at first. If the model is wrong, the system still finds the correct winner. It just takes a bit longer. Security is a paramount concern in decentralized systems, and Zeno-Energy handles this through a strict safety boundary. The energy module is kept entirely outside the consensus-critical trusted computing base. This is enforced by a one-way dependency. Specifically, source energy points to the uniform batch clearing core. The core code does not depend on the energy model. This leads to the fundamental safety property. Notice what this means. Even if the model assigns a low energy to a bad candidate, if the verifier rejects it, the settlement is rejected. Essentially, the model score only influences the order of verification. An attractive model score can change the order of checking, but it cannot authorize a settlement, mutate the ledger, or replace the deterministic verification. This ensures that the system's integrity is never at the mercy of a machine learning model. The architecture of Zeno-Energy is grounded in the lineage of energy-based models, or EBMs, popularized by Yann LeCun and his collaborators. In a general EBM, the model assigns a scalar energy to configurations of variables. During inference, we search for the configuration with the lowest energy. We distinguish between configurations. Undesired configurations get high energy, while desired configurations get low energy. During training, we shape the energy surface. We pull the energy down for desired configurations and push it up for undesired ones. Zeno-Energy specifically uses the discriminative, structured output part of this lineage. It functions as a ranking function that evaluates partial states, which, in our case, are candidate settlements. The constraints in this framework are the verifier obligations, and the objective is the early discovery of the deterministic winner. By framing search as energy minimization, we turn a hard discrete selection problem into a learnable ranking task. The Zeno-Energy model is designed to be incredibly lightweight and efficient. The default model is a simple linear ranker. It uses only 96 feature weights and one bias term, totaling 97 parameters. The energy score E of theta for a context X and candidate C is calculated as W transpose times phi of X and C plus B. Because it is so small, it can run on a CPU without heavy libraries like PyTorch. To train this model, the paper uses a pairwise hinge ranking loss. The loss L is the maximum of 0 and M plus the energy of the good candidate minus the energy of the bad candidate. This loss function compares two candidates from the same batch. It penalizes the model if a good candidate, one with a higher objective, has a higher energy than a bad candidate. To make the training even more effective, the researchers used weighted pair updates. The pair weight is determined by an indicator function for the winner pair multiplied by lambda w plus lambda v times the normalized volume gap plus lambda s times the normalized surplus gap when volume ties. The weight of each training update is adjusted based on the volume gap and surplus gap. This places more training pressure on hard cases, like when a valid candidate is ranked just ahead of a slightly better winner. This forces the model to learn the fine distinctions that matter most for profitability. To test the model, the researchers created a synthetic candidate generator that simulates a single-pool constant product market maker environment. The generator samples everything from user balances to price ratios, creating various families of candidates. Notice that it doesn't just generate good candidates, it generates many types of invalid ones, like those with negative reserves or malformed fill vectors. Every single one of these candidates is labeled by the deterministic verifier. This creates a rich dataset where each row contains a 96-dimensional feature vector, its verifier validity, and its objective metrics like volume and surplus. This robust labeling ensures the model learns not just what a good settlement looks like, but also how to avoid the expensive mistakes that the verifier would inevitably reject. The researchers didn't just write code, they used the lean theorem prover to record formal contracts for safety. Let's review the 3 layers of formal safety. The first layer is exact generation. A mathematical optimality claim only holds if the candidate corpus is sound and complete. The second layer is advisory reordering. This theorem proves that if our ranked list is just a permutation of the original set, the verifier still finds the same global optimum. Reordering for speed doesn't change the final answer. The third layer is the full fallback. It guarantees that if the search goes through the entire reordered list, it is mathematically equivalent to the original exhaustive search. Finally, there is the concept of the early stop. To stop searching before the end of the list, we need a checked stop certificate. This certificate proves that the current winner dominates all remaining unchecked candidates. Without this certificate, we must check the full list, even if the model is very confident. The experimental results are where we see the real power of Zeno-Energy. Let's look at the holdout performance on nearly 2,000 winner-bearing batches. Look at the mean calls column. In a random search, we need over 10 verifier calls on average to find the winner. A hand-coded heuristic gets that down to 1.3, but the learned model gets it down to just 1.017. This is a 94.9% reduction in search cost compared to exhaustive ordering. Furthermore, the model placed the exact winner in the top 1 position in over 98% of cases. And in 100% of cases, the winner was within the top 2 candidates. This means that in a real-world system, you almost never need more than 2 verifier checks to find the best possible trade. To understand why the model works, we can perform an audit of its weights. The largest positive weights, which increase energy and thus lower priority, are assigned to hard verifier-shaped penalties. This makes sense. If a candidate violates basic rules, the model gives it a high energy score to move it to the back of the line. The largest negative weights, which decrease energy and increase priority, are assigned to objective metrics like normalized executed volume at negative 58.01 and normalized surplus at negative 28.77. The model has learned that candidates with high volume and high surplus are the most likely winners. By assigning these features large negative weights, the model ensures that high-value trades are checked first. This confirms the model is acting as an advisory tool, prioritizing what matters most to the DEX. While the results are promising, the paper is transparent about why this is not yet production-ready. There are several engineering and assurance blockers. First, the evidence is still synthetic. We need to see how the model performs on real-world order flow and replay data. Second, the proof of candidate family exactness is still a proof obligation. We need to be mathematically certain that the set of candidates we are searching is actually complete. Third, the scope is currently narrow. The experiments only covered single-pool, exact-in swaps. Real-world trading involves multi-pool routing, confidential order flows, and adversarial behavior like latency races. Finally, operational controls like model artifact signing, version pinning, and drift detection are still missing. These are the guardrails needed before letting an ML model touch a live financial system. Interestingly, the Zeno-Energy pattern isn't just for settlement. It can also be transferred to systems like AutoTrader. If we represent AutoTrader decisions as finite candidate plans, we can use the same model proposes verifier decides logic. Let's show a trading state S mapping to a candidate action set A of S. An advisory scorer can rank these trading strategies based on their utility, while the execution rule remains a deterministic gate that checks for risk, authorization, and budget. Just like in Zeno-DEX, the model would rank the strategies, but it could never authorize a trade on its own. The same safety rules would carry over. The model output never enters balances or state routes, and an early stop would still require a deterministic certificate. This shows that energy-based ranking is a versatile tool for any high-stakes search and verify problem. In conclusion, Zeno-Energy demonstrates that a remarkably small 97-parameter model can fundamentally change the efficiency of decentralized settlement. This model achieves a 94.9% reduction in search cost, ensures the winner is in the top 2 for 100% of batches, all while maintaining a tiny CPU-only footprint. By separating the proposal phase from the verification phase, we gain the speed of machine learning without losing the ironclad security of deterministic code. The path forward involves integrating real-world replay evidence, completing formal optimality certificates, and expanding to AutoTrader candidate planning. The release path is clear. Maintain the model as an advisor, verify everything, and use learned energy to find the best solutions faster. Thank you for joining this deep dive into the future of efficient, verifier-preserving search.